Hello, welcome everybody. This is a webinar brought to you by the Institute of Transportation Engineers, Australia and New Zealand section. And the topic today is travel behaviour and traffic safety. So I'll be the moderator for the day. My name is David Nash. I'm the Secretary of the ITE and would like to welcome you all. We'd also like to do an acknowledgement of country. And the ITE-ANZ acknowledges the Australian Aboriginal and Torres Strait Islander peoples as the first inhabitants of the nation and the traditional custodians of the lands where we live, learn and work. We pay our respects to elders past, present and emerging. We acknowledge and respect the Treaty of Waitangi and Maori as the original people of Aotearoa, New Zealand. Just in case you don't know much about the ITE, it's an international membership association of transport professionals, and we work to improve mobility and safety for all transport system users and help build smart and livable communities. There are about 17,000 members of the ITE around the world. Most of them are in North America. We in Australia and New Zealand are a smaller outpost, but nevertheless an influential one. And new members are always welcome. We'd like to thank our sponsors who are listed there on the screen there. Due to their generosity, we're able to bring you these webinars at no cost to participants. Today's presenters are two professors from the Queensland University of Technology, Professor Alex Paz and Professor Shumal Haq. So we look forward to their presentations today. Just a couple of housekeeping things. You'll be automatically muted, so make as much noise as you like in the background. We won't be able to hear you. If you have any technical problems, send a message to us via the chat. And after the presentations, after both presentations, there'll be a period of time where there's a question and answer session. And if you've got any questions at the end or any time during the sessions, just press on this Q&A button to put your questions forward. So these are our two presenters, and the first one will be Alex. His topic is the estimation of travel behaviour and crash models using optimisation. So just a quick introduction of Professor Alexander Paz. He's from the School of Civil and Environmental Engineering at QUT, where he's the Transport and Main Roads Chair. As well as being registered as an engineer in Australia, he's also licensed in the state of Nevada. He has a strong background in transport engineering, travel behaviour, transport planning and road safety. His significant experience in developing methods, algorithms and software tools for the management and analysis of highway infrastructure and the deployment of intelligent transport systems. Some of his work has been adopted by industry and some have been patented as well. He received his PhD in Transportation and Infrastructure Systems from engineering from the Purdue University, which I believe is in Indiana. So over to you, Alex.
Thank you very much, David, and thank you very much for this opportunity. I'm going to be presenting the work of my two PhD students, Prithbit Viramole and Sig Aher. They both have been working in parallel on developing optimization frameworks to support the estimation of data count models. Prithbit has been focusing on discrete outcome models, which have application on travel behavior, as well as crash severity analysis. And Sig has been focused on crash frequency models. And my presentation is about statistical modeling. We are not considering here machine learning or any of those data-driven methods, and we have reasons for that, but I will leave it for another presentation. So a little bit of background before I go to a little bit of motivation before I go to the...
Alex, have you shared the screen?
Oh, you're not looking at my screen now. Sorry. Yes, it is, but let me do it again. So a little bit of motivation while I share my screen. Can you see it now? Can you see it now?
Yes, we just go to full screen mode. That's it.
So again, a statistical analysis. Whenever we are estimating regression models, the analyst needs to make a number of decisions. These decisions are assumptions that represent hypotheses that need to be tested. Some of the decisions include what factors to include in the models. Maybe we want to test some transformations to better capture the trends in the data. Oftentimes, there are correlations that we need to manage. And again, oftentimes we need to capture unobserved heterogeneity or random taste variation in the data. And we need to make assumptions about the distribution of the error terms so that we can estimate the models. All of these decisions are interdependent, and significant statistical analysis and testing is required to find the best model structure and the best model to make inferences. This process is time-consuming, again, requires significant statistical knowledge as well as expert problem context knowledge. So the process is open and has the risk of bias, human bias, as well as errors and misspecifications. And I'm going to show you some clear examples about this. The problem becomes even worse when we need to estimate multiple models. I'm providing here two examples. One of them is in the context of activity-based models. These are relatively advanced travel behavior models that require multiple mode choices. Multiple travel behavior models to estimate modes, destination, departure time, activities, among other choices. Oftentimes, also in road safety analysis, the agencies are interested in models for a specific vehicle type, facility type, and crash type. And you combine all the options that you have there, you can end having hundreds of models for a single region. Consequently, the job of estimating these models becomes quite time-consuming, and that creates opportunities for error and misspecification. The problem is even worse when we try to estimate integrated models, where multiple choices or multiple outcomes need to be considered simultaneously. And the main motivation for this is to increase realism. So again, the task becomes very involved. To support during the estimation of these models, what we are proposing is the use of optimization, so that we use software and hardware to perform an extensive search, an extensive hypothesis testing, and that will decrease the chances significantly, the chances of misspecifications, and increase the chances of getting more information from the data. So we have proposed a multi-objective, nonlinear, mixed integer programming optimization framework with mostly two objectives. The first one is to maximize the in-sample explanatory power, and the second is to maximize the out-of-sample prediction accuracy. And we seek these two objectives simultaneously while also considering in the hypothesis testing generation process the combinations of likely contributing factors, transformations, unobserved heterogeneity, associated distributions that are required to capture that heterogeneity, and correlations. I'm not going to go into the details of the mathematical programming formulation. I'm just going to highlight a key components. The first one is the two objectives that I mentioned to you before. One is the minimization of the Bayesian information criteria, which is quite commonly used for estimation of this type of models. And the second one is the minimization of the mean average error, or absolute error, sorry. And we, again, seek to minimize these two simultaneously. And we also have a number of constraints. For example, here I have a transformation, which is the box-Cox transformation often used in travel behavior modeling. We also have constraints to include expert knowledge in the modeling process. And this allows us to introduce specific hypotheses that we want to test or we want to include during the development of the models. Now, the problem is NP-hard is not convex. The objective functions are not linear, and we have a relatively large number of decision variables with different characteristics. So we look in the literature for potential algorithms to solve the problem. And we also look at the work that we have done in the past. And in the past, we solved a similar problem for the calibration of microscopic traffic flow simulation models. What we did is we tested 17 meta-heuristics commonly used for the calibration of these models. And we found one highlighted here with red color, the multi-objective global best harmony search, which is number 8 in this list of 70 meta-heuristics. Each row represents a meta-heuristic, and each column is being used to compare all of them, right? So a solid dot or a solid circle here means a dominant solution or a dominant algorithm. And as you can see here, the multi-objective global best harmony search dominates all the other meta-heuristics for this particular problem, which is not exactly the one that I'm presenting today, but has similar characteristics. And for that reason, we decided to test if we could solve our optimization problem using this meta-heuristic. So we implemented the meta-heuristic in Python, and we are providing open source access to the meta-heuristic. So if you like to test it, you can search for search logic. That's the name that we gave it to the algorithm. Or you can use the link that I'm providing here. And we, of course, also have some publications. This is relatively new work. The students haven't completed their PhD, so some of the papers are under external review. But we already have some that can give you details, sufficient details about the problem, as well as the implementation of the solution algorithm and results. So to test how good is our proposed framework, we look into the literature, and we look for literature that also provides open source access to the data. And I think there is a question here. Oh, okay. So we look at multiple examples of papers where we can see models, and we can re-estimate those models using the same data. Some of them are published by leader researchers in the field, such as Michel Valliere, listed here, and Kenneth Train from Berkeley. So we are benchmarking our models, our framework, using multiple models from multiple people, and some of them are leaders in the field. And in all the cases, we are showing that our framework is able to get better goodness of fit, but also capture some insights that are important and were not captured by the published work. We also tested our framework using synthetic data. And the advantage of using synthetic data is that we create a model, a relatively complex model with different characteristics that we want to have. And we generate the corresponding data, and we use that data to run our optimization framework and see if it is able to replicate the model that we have created. This, of course, is very interesting and important, because we know, unlike the actual data, in this case, we know the behavior that we have created. So we can benchmark our outcome and see how far we are from what was created. So I can move. Oh, here we go. So the first example that I'm going to show you is using data from Brisbane. It is a mode choice problem, 7 alternatives. We have attributes for those alternatives, and we have socioeconomic characteristics, about 4,900 observations. 67% are used for training, and 33% are used for testing. In the horizontal axis here, I have the first objective function, the Bayesian information criteria. And in the vertical axis, I have the mean absolute error. And I am also showing you here the benchmark model from literature with the red start. These are initial solutions that are generated by the solution algorithm. The blue ones are all the solutions that are considered during the search of the optimal solution. And the orange line represents the Pareto front, those solutions that are not dominated in both cases by any other solution or in both objectives. And there is a solution in particular that we have chosen because it has lower BIC and lower MAE. So basically it's better relative to the two objective functions compared to the benchmark solution. The models are relatively large. I'm showing you here only a portion of them. The one in the center is the specification from the literature. And the one on the right-hand side is the one that we are estimating. They have multiple differences. I'm highlighting here with blue travel time to explain a particular interesting difference with significant behavioral implications. If you see our model include a lambda of 0.5, that is part of the Box-Cox transformation for travel time that our model finds to be important. And if we look at this graph, in the horizontal axis, we have the additional travel time in minutes. And in the vertical axis, we have the probability of choosing to drive for shopping trips in Brisbane. The blue curve that you see here is the one using the model from literature. And as you can see at the beginning, as travel time increases, so is the probability of driving, which makes sense for shopping trips in Brisbane. But after 40, the probability decreases, and it decreases significantly. It goes from about 67 to a little bit less than 50, which is a significant change. And it's not intuitive. Actually, we wouldn't expect that as travel time increases in Brisbane, people prefer to switch to other modes that are not driving, such as transit. We wouldn't expect that to be the case. We will expect that either the probability does not change, or actually people are more likely to drive for shopping trips. When we use our model, because the Box-Cox transformation factors for the effect of the scale of travel time, we see that there is not much change on the probability of choosing to drive. It doesn't change that much as expected. So these results, combined with a better BIC, are sufficient for us to conclude that our model is superior to the one in literature. The second example that I'm going to show you is using data from Switzerland. It is a relatively well-known data set. The Swiss Metro data set. It is used in multiple publications. 3 alternatives: car, train, and metro. Information about the attributes of these alternatives, as well as socioeconomic characteristics. There are more than 10,000 observations. We use 20% for training, and 80% for training and 20% for testing. These is a similar graph to the one that I showed you before. Horizontal axis is the first objective function, BIC, and the vertical axis is the MAE. The benchmark solution, as you can see there with the red star, is quite high and almost in the center of the graph. And we have many solutions that are better considering the 2 objectives to this benchmark solution. We also have the Pareto front in orange as before. And as you can expect, given the significant difference between the benchmark solution and the ones in the Pareto front, the models have significant differences. So I am providing here only a portion of the 2 models and I providing two utilities, the one for metro and the one for car. Quickly, you can see that our model includes lots of random parameters, while the model in literature does not include random parameters. You can also see at the bottom that our goodness of fit are significantly better than the ones in literature. And just in case, regarding overfitting, we are using the BIC, which penalizes for adding variables into the model. We explicitly have selected this criteria for that reason. So there is no chance of overfitting here. Plus, we are considering multiple objectives. There are many things that I could tell you about behavioral inferences from the two models, but I'm gonna show you one quite important, and that is the willingness to pay. You can see there that in blue, the willingness to pay that is calculated using the model from literature. And according to the model from literature, people will be willing to pay 17.6 Australian dollars. I have translated to Australian dollars so that is easier for us to understand. 17.6 Australian dollars for 1 minute of travel time and 17.6 Australian dollars from 1 minute of headway. Clearly, that doesn't make sense, right? That people will be willing to pay that much in Switzerland for saving travel time. If we use our estimates, the people are willing to pay about $1 per minute of travel time and about 1 cent for minute of headway. These are way more reasonable values. So this type of inferences that we can make with our model that are more reasonable, along with the goodness of fit, make us conclude that our model is better than the one in literature, or at least is presenting to the analyst results that should be considered. The final example that I have is about crash frequency analysis. We are using data from Washington State, 275 segments, data from 1990, 5 years of observations, 30 potential contributing factors, more than 4,000 crashes. There are 17 segments with 0 observations. The average crash per segment is 16, and the maximum segment length is 31 kilometers. The model in green is the one from literature. The model in yellow is the one that we are estimating. Again, the models are relatively larger than much larger than what I'm showing you here. I'm just showing you a portion of the model for simplicity. First of all, the goodness of fit are significantly different, better in both cases, log likelihood as BIC for us, the model that we are estimating. And I'm going to highlight a couple of key differences. In red, you will see there the coefficients for average precipitation or rainfall. The model in literature is telling us that as it rains, the more it rains, the less safe are the overall segments. Our model, I think there is a question, 1 second. Maybe I respond to the questions at the end. Okay, so sorry about that. I was saying that the model in literature is telling us that the more it rains, the less safe is the network. The model that we're estimating has a negative coefficient. So it's telling us that the more it rains, the safer it is. However, there is a caveat here, and in both cases, there are random parameters. And the magnitude of the standard deviation is relatively large compared to the mean. The mean is the one in red, the standard deviation is the one in black, which means that for some segments, in both cases, the more it rains, the less safe it is. We look in the literature and we found a few references where the results are similar to with our negative coefficient here for the mean, which again is saying the more it rains, the safer it is. And the explanations for that were that people drive more conservative, basically. There is less driving and people drive more conservative. So that explains the negative sign consistent with other references. But again, we also have a random parameter and a large standard deviation. Something even more important is correlated parameters. If you see here at the bottom of the table, we have correlated parameters between local roads and average precipitation. And this random parameter is significant, which means that when it rains, the safety of local roads decreases significantly. And this is something that was not found in the model from literature. Either the team did not check for correlated parameters, or they were not able to find them significant. In any case, our proposed approach, because it's performing an extensive search and extensive hypothesis testing, is able to at least flag these characteristics of models that can be captured with the data and provide significant inferences that the analyst should consider. So in summary, I have described to you an optimization framework for the estimation of data count models, both discrete outcome models and crash frequency models. We use multiple objectives, and we simultaneously consider many important modeling aspects that should be considered, such as the one that I'm listing here, and I described it to you before. In the future, we would like to include latent classes as one more dimension or aspect that we would like to investigate simultaneously with everything else that I have shown you. We will also like to test if our framework provides similar results using crash severity data, using the discrete outcome models. And also we like to explore other paradigms beyond random utility maximization, especially in the context of latent classes. There may be some classes that follow random utility maximization, and others may follow something such as regret minimization. I'd be happy to answer questions after my colleague Shimul provides his presentation.
Excellent. Thank you very much for that, Alex. And Shimul, if you'd like to share your screen, I'll just introduce you while you're doing that. So Professor Shimul Haq is also part of the School of Civil and Environmental Engineering at QUT. He's Professor of Transportation Engineering and the Director of the Smart Transport Safety Research Lab. He's passionate about road safety and is a specialist in econometrics and artificial intelligence applications. His research is focused on developing intelligent technologies to save lives and reduce road traffic injuries through efficient and low-cost countermeasures. He is an associate editor of the journal Analytical Methods in Accident Research and Accident Analysis and Prevention. He co-founded the university-led startup Advanced Mobility Analytics Group, or AMAG for short, which provides a world-leading platform in transport analytics. So over to you, Shimul.
Thank you, David, and thank you, ITE-ANZ and Sarah Moritpur for inviting and giving this opportunity to talk in this exciting platform. So today I'll be talking about artificial intelligence-based video analytics for road safety evaluation, where I'll try to cover quickly in my short period of time that where we are in terms of the research and what we are doing to applying this research to tackling various road safety problems. First of all, just to give you a background, what we have been doing until today to address safety challenges, we have mostly using the accident or crash data, which are very rare and random. So that we always need to wait for the crashes to happen so that we can make some safety judgment or safety evaluation or assessment. So now it creates lots of problem, both ethically and of course that in process-wise. Ethically, that creates a problem. For instance, that you have now improved a transport facility, let's say intersection or highway section. Now you want to know about what happens to the safety. So the best tool that we have until today, we need to wait for crashes to happen or no crashes to happen so that we can understand what is happening in terms of the safety. In other words, we are waiting for people to die or injured in the road so that we can make a judgment about the safety of that particular transport facility. To overcome these challenges, traffic conflict techniques have been developed over the years, and these days it is getting more momentum. So if we compare the traffic conflicts and the crashes, sometimes we feel that the difference between the traffic conflicts and crashes is probably less than a second. But this, I think this is not the sole idea. Our whole idea here is that, that all the traffic events in a road facility or road network, it follows a safety pyramid or hierarchy of the traffic events, where the crashes are at the top of the pyramid, or it is just the tip of the iceberg that is visible to us, and we collect the data and see them. And for the traffic conflicts and other things that we don't capture, that's what we don't see. We collect lots of course information through the loop detector or some survey like traffic volume, speed, and etc. But we really don't capture the interaction. Then in the interactions, we can see that there are lots of things that are happening. That could be some serious conflict, that could be some not so serious conflicts. But in the safety that we have demonstrated that all of those things have do carry meaningful information that can be used to estimate safety. Okay. So the idea here is that if we can develop the relationship between those traffic conflicts and the crashes that we see in the tip of the iceberg, we should be able to accurately predict the crash risk to appropriate modeling technique. And again, if we can select the appropriate traffic conflict indicators and develop an appropriate model, we can even estimate the crash risk by the injury severity level. And this is the talk all about that I'm going to cover, that what we have been done in this area to establish the relationship between the traffic conflict and crashes. So first of all, before we do this work, what my group has done, we took up the challenge to actually review almost all the studies that's published in the literature regarding the use of the traffic conflicts. And we have, for the last 10 years, more than 650 papers published in this area in leading road safety journals in English. And after we have reviewed them, we found that actually that the concept has not been very clear, how to define conflicts and how we can capture the crash risk through the various use of conflict indicators. And by and large, we are missing one of the big component, what is the context. For example, there one sort of traffic conflict measure that is applicable for the signals may not be applicable for the highway section or weaving sections, but those kind of things have not been captured very well. And of course, that there are some modeling issues like that. No consideration of the heterogeneity and crash severity. I think Alex has also covered a lot that the importance of considering the random parameters or unobserved heterogeneity in the econometric model. So again, another challenge that we have seen, the sensing technologies for traffic data collection is changing so fast. We started with the loop detector many years ago. Then these days, with the improvement of the computational technology, now we have radar, LiDAR, heat sensor cameras, video cameras, and you name it. There are lots of technology. In fact, there is a separate project going on where Alex, Ashish are leading, that what kind of technology that we use for traffic data collection, that is huge, But the question is that if you get those granular level of information from those traffic environment, how we can develop meaningful insights into safety utilizing those information. So this is the challenge, and this is what we are going to talk a little bit more. So in this talk, we'll be mainly talking about the video data that we have been using explicitly for our traffic safety analysis. The reason that we are using the video data, of course, that compared to all other technologies, because until today, it provides most accurate and granular level information. LiDAR provides wide coverage of information, but it has limitations in terms of identifying the road user classes, and accuracy is compromised. So until today, we have seen that video data provides a good solution, but as I said, that a comparative study needs to be done. So today we'll be talking about how we have utilized the video data for doing road safety research. Once we get the video data, first thing that we have done, we have to detect and track all the road users accurately. So this is the work that we have been doing for many years to perfection it, to improve this method, improve this detection and tracking algorithm, to identify the various road user classes. So now we have tested rigorously and everything. We can capture around the road user information with a 99% accuracy. So we can classify all the road users that's provided by the OSTROS, 13 road user classifications. In fact, Now we have also trained our model that can classify whether a pedestrian is walking alone or pedestrian is walking with his or her dog. So we have gone through that level of information. Of course, the other road users, as you can see from this video that I have shown from the various projects in the past, we can identify them quite accurately and reasonably well. So, but this is not the end of the problem. Actually, for road safety research, this is the start of the problem. Once you get all those tracking and all those trajectories, how you are going to convert them into the meaningful road safety outcomes or road safety assessment metrics. So one thing that we have developed a procedure here in this procedure, what we do, we convert or we detect all the road users, trace them accurately, then we need to map them into the real world trajectories, real world map, and identify all the conflicts, because to map them in the real world coordinates is an important step, because then we can pinpoint where those problems are happening. So as I said that, if we can pinpoint those problems, actually from any kind of road network or any kind of road transport facility, we can pinpoint where those crashes are or conflicts are happening, where the risk is high. Unlike crash data provides an information like for an intersection A has X many number of crashes, but actually where in that intersection is the problem. They provide some directional movement, but still it's not very accurate. So with this conflict information, we should pinpoint them and can develop the heat maps and others that can actually pinpoint the locations of the conflict that's happening. So as I said, that as David mentioned, that we have now actually this a whole procedure that we have been working for many years, more than 10 years now. We have been successfully conveyed to a university-led startup, which involves University of Queensland, Professor Simon Washington, myself from QUT, and Professor Tarek Said from University of British Columbia, which actually offers lots of in-depth safety analytics, for from the processing the video data. But again, as I said, that this is just the data. Now, in terms of the research, how we can translate into the risk or estimate of the risk that can provide meaningful insights and can help generating actionable items for road authorities to mitigate safety problems. So we have for this work, there are lots of modeling options available. For today's talk, I'll be talking about extreme value theory or generalized extreme value model. Actually, what it does, actually, it takes the maxima of different blocks, traffic conflicts, and develop a model and establish a model so that you can predict the crash risk that you are not observing. So it is a forecasting mechanism. And this model can also take into account heterogeneity problem, like it can take into account exposure, it can take into account various road user classifications, road users interactions, road geometric characteristics, speed characteristics, everything, so that it can give you those granular level of crash risk based on the different composition of the traffic that we have. Okay, so let's start talk about some of the case studies that quickly that we did with these traffic conflict techniques. So that we, first of all, we take this one, the most prominent crash type is the rear end crashes along the road network. So we have taken the intersections. So we need to estimate the rear end crash risk from the traffic conflicts and validate it, whether we have accurate conflict measures that can correlate conflicts with the crashes. So we have taken modified time to collision. By the way, there are more than 150 traffic conflict indicators available in the literature that everyone claims it to be best. Of course, when you develop, it's novel, but we have done a rigorous test to identify what kind of traffic conflict indicators can provide and provide the results probably, and we have validated that for in the context of developed countries like US, Canada, and the Australian condition, but may or may not work in developing countries. It needs different types of conflict indicators. But here in the project that we have done in the state of Queensland for a number of sites, and develop the relationship between the traffic conflict and crashes by taking the modified time to collision, which is again time to collisions, like if the two roads are in a collision course at time point, how long would they take to meet and collide if they continue through their path, and modified time to collision because we have also taken into account the relative acceleration, which was not been accounted for in the past. Then, of course, that just getting the crash frequency is not enough. We also need to estimate the crash frequency by the severity level, because government authorities often look for, fatal and serious injury crash risk rather than the non-serious injury crash risk, because this is how they can develop the targeted countermeasures. And actually, they're fortunate enough, traffic conflict technique, if we use appropriate indicator, that can also offer a good estimate of the crash risk by the severity level. Here we have proposed post-collision velocity difference, delta V, which is again a surrogate measure or conflict measure. It's defined as a change in the velocity between the pre-collision and the post-collision trajectories of the vehicle. So, and it is again, it is observable from the video data. Once we take this one and apply the extreme value theory model, I have avoided this mathematical discussion here. But once we have put this on, what we have tried to do that we have estimated the crash risk by the severity level for the data set for 5 intersections that we are talking about, 5 multiplied by the 4 intersection, 20 intersection approaches here. So in the left one is the observed crashes. You can see this is observed. And in the model, I did not touch the crash data set to predict the model. The observed crashes in those intersections, observed crashes per year. That's why numbers are like that. And the orange one is the severe crashes, and the green one is the non-severe crashes. You can see that in the last column, you can see these are all the modeling options. Last column, when we applied a bivariate extreme value theory model with the modified time to collision and post-collision velocity, and you can see that it can reasonably predict the historical crash record that has been of the last 5 years, just observing the traffic conflicts for a week. So you understand that that is the strength of this relationship. By observing the traffic conflicts only for a week, we can get a better sense of the safety risk that is happening at the site. So it opens up the door. Now, if this is the case, it opens up the door to develop mitigating action before they turn into a crash. Then we have given that after validating the model, what we have done, because we need granular level information now. We have also predicted the crash at the signal cycle level, so that now we can accurately predict that, of course, that which signal cycle level are risky compared to the unrisky one based on the traffic interaction that we have. And again, it has been validated for a week of the traffic conflict data. Then we predict it for the next day or next signal cycles. And we found that actually the traffic conflict, of course, the rear end crash risk varies across the day. It is not uniform throughout the day for site, varies. Usually for rear end crashes, in the peak hour, we have got more crash risk. We understand stop and go situation, and off peak hour is less, which is quite obvious. Then we have taken up this model to estimate the crash risk for pedestrians now. Okay, and when we talk about the estimating the pedestrian crash risk at the real time, we could not use those indicators that we have developed for rear end crashes. We needed to develop a completely different set of traffic conflict measures, and which we did, and try to estimate the crashes of the pedestrian crashes at the signal cycle level, and try to see that what is happening across the site. We thought that the pedestrian crash risk will be higher when there are lots of pedestrians on the road, but actually the results are completely opposite. We found that actually pedestrian crash risk is higher when the traffic volume is less, or not. So pedestrians are not traffic volume. Pedestrian volume is less. So that when the lots of jaywalking is happening, lots of violations are happening, and which actually elevate the crash risk. So now you know that if we can estimate the pedestrian crash risk at the signal cycle level, we can develop some targeted countermeasures to mitigate the problem. And I'll be talking about a couple of case studies on that matter if I get time. So again, and one other thing that we have been working these days, that once we get the pedestrian crash risk, but let's say that you are putting a video camera, we are getting the data and processing it. By the time we get the data and process it, it is already too late, no real time anymore, right? So that we needed to develop a methodology so that if we see that whether we can forecast the crash, forecasting the crash risk, whether it is possible. I'm talking about those systematic crash risks that gone up in that site. And we have developed a machine learning model, a recurrent neural network model. And we have found that actually we can predict the crashes up to 15 to 20 minutes reasonably well. It means that we have 10 to 15 minutes of the time that can be used to mitigate, develop actionable items. We can do leading pedestrian intervals or develop other countermeasures to tackle this safety problem. So now, which gives you a way to talk about a couple of the case studies that we have done. So this is the project we did participate in the city of Bellevue, Washington, in the US. So city of Bellevue has converted those installed leading pedestrian interval signals to improve pedestrian safety. And they're interested to know whether this is an effective methodology, effective mitigation method. What it does, leading pedestrian interval, that, for example, that right turners, for the case in Australia, is left turning vehicles and the pedestrians got the green cycle at the same time, which creates a problematic, so that they try to say that, okay, if they give an headway to the pedestrian starts 5 seconds early before the vehicles, left turning vehicles get, or in this case, right turning vehicle get the green signal. The leading pedestrian interval, they have installed that leading pedestrian interval for 6 pedestrian crossing, and we have also taken some 4 control approaches and collected the data before and after the intervention. And the city of, I collected the video data from their existing CCTV network and processed this one, and actually found that actually by this applying this traffic conflict technique, developing this extreme value theory model, estimate the crash risk, validated with the historical crash record, we found that this technique can reduce 43% of the vehicle pedestrian crash risk that is happening with the left turning vehicle, or in this case, right turning vehicles and the pedestrians. And there has been no change in the rear end conflicts for this treatment. So again, it becomes a useful treatment for them. So then now they are thinking of going into citywide and do a proper, even wider evaluation of this technique, of these countermeasures. Another one, this is the before after evaluation of the part-time protected right turn signal. This is the project that we recently did here in Queensland. Why it called part-time protected right turn signal strategy? Okay, part-time right turn signal strategy means that if you have a signal system where we have permissive right turn signal during peak hours and protected right turn signal, fully protected right turn signals in the off-peak hours. Okay, why? Because if you talk to the safety people, they say that, okay, a protected right turn signal, of course, it has lots of safety benefit. They want to install a protected right turn signals throughout the intersections. But if you talk to the people who are talking about the capacity, throughput, minimizing the delay, they say, no, it is going to increase our queue length, increase our problems of delay, and that would not sustainable. Then they come up with a solution. Let's say, how about your problem is mostly in the peak hours, you keep permissive right turn signals in the peak hours and give us the opportunity to put a fully protected right turn signal in the off peak hour to find a solution that's in between. So we have implemented this one at the city of Cairns for 5 intersections. Actually, they treated 7 intersection approaches and 4 control approaches. We collected the data 1 week before and after. Some of the data that collect from the existing TMR video cameras, and these are the sites. And then we have done a proper evaluation. At first, of course, that once they have implemented this technology, you can see that from the heat maps, all the right turn conflict or opposing turn conflict have been reduced in the after period for all the intersections. For all the intersections that has happened. Now, this is not enough. As I said, the traffic conflict is merely a conflict measure, but you really need to estimate the real crash risk, because not all the conflict data have meaningful relationship to the crash risk. So again, we have developed a methodology and developed a model that estimate the crash risk with the traffic conflicts. I'm not going to the technical details, but we have developed a bivariate extreme value model, and we have estimated the crash risk by severity. After doing this and applying this technology, we have compared the before-after, doing the before-after evaluation of the part-time protected right turn signal. We found that actually right turn crash is reduced by 72%, just by implementing this treatment for the off-peak hours, and its severe crash is reduced by 66%, 2%. So that it offers a good solution. But another question is that what we are doing in terms of the performance of the intersection. Okay, we have also captured the queue length of that intersection of those treated approaches. We found that actually during the permissible period where we have that the protected right turn period, we did not find this period, protected right turn period, which is the green one. We did not find the queue length has gone up to the queue length of the permissible right turning phases. So it means that average queue lengths are okay for those treatments being for those approaches being treated, so that it offers a good solution balancing between the safety and efficiency of that intersection. After that, so that is takeaways for today. So of course, traffic conflicts provide a reliable estimate of road safety without waiting for crashes, proactive methods, and we can also offer real-time road safety statuses or risks. And as I have demonstrated that it opens door to develop smart technology solution to reduce traffic crashes and injuries. Thank you for your time. So over to you, David, and we're happy to take questions.
Excellent. Thank you very much for those two presentations. We've got a few questions here, so maybe the first one could go to you, Shimal. Why is crash data-based analysis unethical, which you mentioned earlier in your talk? Surely this is simply a case of making best use of data available to practitioners at the time.
So I think that, look, Toby, thanks for this question that you have asked the right question. Yes, at this moment, we have this crash data available because this is the best that we have right now. But if we think as a scientific researcher, you know, as we talk about a researcher, and you let's say that you ask me to do an evaluation of a site being treated recently, you know, that I don't have any option to treat or to evaluate that site, you know, without waiting for the crashes. If I need to wait for do the crash data analysis, like that's why I say that in other words, you know, if I take away all of our professional, you know, professional boundaries, if you take other words, we are waiting for the crashes to happen, and so that we can make a better judgment of what has happened to the road. So from that point of view, we call it as, you know, as a human. I understand that as a professional wise, that's the best way that we can do. We have left out with no option at this moment, you know. But that's why I say that, you know, that it is probably from the human point of view, it is not ethically correct, you know. But given that we are now going with the technologies coming, we are getting more data, you know, so that we can best use of the other metric that is available rather than waiting for those crashes to happen. So this is what I meant. Okay, over to you, David. There is another question. Do you want me to go?
Look, we'll swap over to Alex now, just
sure.
to give you a rest. There was a question here, Alex, about how travel behaviour affects the design of urban transport systems in terms of managing rush hours. Have you got some sort of answer to that question?
Sure. Look, the agencies, the transport agencies, they regularly collect travel behavior data, household travel survey data typically, and they use that data to create a number of models. And they include those models into what they call strategic travel demand models. That's one particular business area or activity that the transport agencies have, right? Especially for large urban areas. And those models are used for long-range planning, highly motivated by congestion, which is probably what rush hours mean in the question. And those models are used to evaluate infrastructure projects, different type of projects, new facilities, new roadways, the adding capacity to existing facilities, maybe building bypasses, maybe introducing more public transport. All of those models, network models, are powered by travel behavior models, but mode choice, departure time, destination, and so forth. So that is the way that the travel behavior, such as the one that I was describing in my presentation, is used. Probably the most common way to use it. I show you an example on willingness to pay. Willingness to pay is often used as a metric, obviously to come up with the pricing strategies for public transport, but also to make decisions. Do we increase? Do we have enough justification to increase or not public transportation?
Cool, thank you very much for that. Back to Shimal, about the camera equipment. Someone says that they noticed the camera equipment is on quite a high pole. Can you share who the equipment supplier is?
For those,
maybe you could put it into the chat.
Yeah, sure, David. For those that are very high up in the sky, it is coming from the TMR's existing CCTV camera footages that they have set it up. So it is from in-house by the Department of Transport and Maintenance in Queensland. And there are some cameras that's not so high. We have gone up to 6-meter pole. For those cameras, one thing is done again by Road Tech here. And so they have provided those poles for this project.
Cool. And back to Alex again. How will you consider the requirements of passengers in designing urban transport of a mega city like Dhaka?
Right. Okay. So in these behavioral models, there are two major pieces of information that are required. One is the attributes of the transportation alternatives. Different attributes, right? Travel time is one of them, but it's not the only one. Cost is another attribute, for example, tolls, fares for public transport. So those attributes are included, are tested, are evaluated, and that comes from the behavior that people discloses, right? The other part are the socioeconomic characteristics, which are obviously information about people, the passengers that you are asking in your question. So the two of them combined are used to develop these models, and the statistical analysis reveals what matters to people and what doesn't matter to people, right? And combine those two aspects that matter to people are used by the transport agencies, or are supposed to be used by the transport agencies to make decisions, right? And that's one of the reasons why we really want to minimize the error in our estimates. There are multiple sources of error, ranging from the data quality to missing information and modeling error. So my presentation was focused on minimizing the modeling error so that we do the best that we can, given the available tools, to take advantage of the data that is collected, which include those aspects about the passenger that you're asking me in your question. I gave you an example again. The willingness to pay will be one key. In a city like Dhaka, I imagine there is lots of public transportation and people have to pay for it, right? I think the only place in the world where public transportation is free is in Luxembourg. So other than that, we all pay for public transportation, and that comes, or supposed to come, from a behavioral analysis such as the one that I provided today.
Cool. Just one last question then for Shimul about regression to the mean. Do these risk estimations take into account regression to the mean, and how does it affect estimates under this method?
Yep, that's a great question, but it will be very difficult to answer in a short time. But let me give you, Maria, that's a great question, and let me give you a quick some of the thoughts that how we have considered the regression to the mean. So for any transport facility, that for regression to the mean, either long mean, you're talking about long-term problem, that how it regress to the mean over the site, you know. So that that's the reason that why we have, for when we have validated the model, we have taken at least 5 years of crash data, so that at least you get a stable mean of what is happening in terms of safety for the site, you know. And we have also captured not only the mean, but also taken into account the confidence interval of that estimate that we observed for a particular site. We have assumed a Poisson distribution, and for the Poisson distribution, we can, based on your level of significance level, we can estimate the confidence interval, which we did. And then we have predicted the crashes from the traffic conflicts and compared to them. So that's the way we have taken into account the regression to the mean difference. But again, if we really need to investigate that problem, I think that we need to look for the longer data set, longer conflict observation, and the longer crash data set. But the real challenge here is that if we talk about the last 5 years, look, we assume that last 5 years nothing has changed in the sites geometrically, right? But if it has changed, probably that we are also getting into another problem. Okay, so that's the way that we have taken into account the regression to the mean by taking actually like last 5 years of the data, and we in the safety literature we have seen that when we consider 3 to 5 years of data, it provides a relatively stable estimate of safety compared to if we just taken into account 1 year of data, for example, which we didn't. So that's the way we have taken into account RTM effect that you're talking about. Thank you.
Okay, excellent answer to that. Thank you very much. So look, I'll bring things to a close at this stage and thank our two speakers for very good presentations, and I'm just impressed at how much data there is there and how much sophistication there is in the models. So thank our two speakers very, very much. And just in conclusion, I'll talk about our next events coming up. Wednesday next week, we're running another webinar involving Leo Steinberg from the Netherlands and Dr. Tom Logan from New Zealand. So two sides of the globe, and they're going to be talking about accessible city planning. So look out for that webinar. And then the next event is on the 13th of September. Professor Hussein Dia from Swinburne University will be talking about smart and sustainable mobility. So we've had quite a few professors in our lineup recently. So thank you very much for attending. In answer to Nick's question, yes, there is a recording, and the recording will be available probably tomorrow sometime if you look on our ITE-ANZ website. So I'll draw things to a close at this stage. If people would like to stick around and have further discussions, feel free, but I'll just stop the recording at that point.